All right, this next problem says that equations 768 and 770 both say that the solid angle going through a duct this fraction is equal to that. Put the dose at a point in the exit plane of a straight duct resulting from the line of sight radiation. So this is a line of sight radiation, anything inside here, from a uniform isotropic incident fluence. So here we have some fluence going on that is isotropic and uniform. And they said that this dose fraction is equal to omega over 2 pi. Show this is true for any cross-sectional shape. So for an isotropic fluence as a function of direction is equal to fluence naught, which is a constant. So it doesn't matter which direction you're going, which direction you're thinking about, you're going to have some fluence as a constant. So this is going to be the angular flow that goes through the duct. If you remember way back, equation 2.17, chapter 2 talks about the flow. J sub n omega is equal to omega times fluence naught. Well, right before they give these two relationships, equation 7.62 says that d naught of p is equal to the response function area integral d omega negative 1 j sub n. Well, if we just plug in j sub n there, we have the dose is equal to the response a delta omega times, delta omega times lowercase omega times Jn, which we said earlier was omega fluence naught. Well, those cancel, and you get that d naught, or uncollided d at some point, is equal to omega fluence. And if this is constant, then it's just pulled out and you just get which this equals this is the same as this. The fluence coming out, the response of it. So all this says is that if you have uniform isotropic fluence, the amount of radiation that gets here is going to be the amount of radiation that can get here from line of sight is just going to be how big that particle, or how big that point P looks in the solid angle. So if it takes up half your solid angle, it's gonna give you, it's gonna receive half of that fluence. It's actually this over 2 pi. But yeah, this one's a real simple one. You just say that you take away the angular dependence of the fluence, and then use one of the definitions for flow, plug that into one of the previous equations in the book, and it comes right out. Anybody have any questions in this one?
How does that last equation equal the other one? I see R and
Yeah.
fluence equals D.
Yeah.
9,
Fluence is in units of amount per second. And remember before, we would say that our dose is equal to flux times the response function?
Yeah.
Well, this would be a dose rate. So our dose is just going to be equal to our fluence times the response function. And that's where this comes from. That's where that comes from.
Okay, so we're dividing that over, and the other 2 pi is just inside of the delta
Yeah.
omega?